Today we'll look at Gauss's law, which is used to determine the electric field where the charge distribution is not straightforward. And the fundamental concept to Gauss's law is flux. So to get an understanding of flux, we'll first look at the analogy of a fluid. So if we have these vectors representing the velocity of the fluid particles, well, the volume of fluid flowing through this surface with some area is equal to the area by the velocity, which is known as the volumetric flow rate or the fluid volume flux. So notice that the units are meters squared by meter per second. So it's meters cubed per second, or in other words, the volume of fluid flowing through that surface per unit time. And similarly, we can have mass flux, for example. So we multiply this volume flux by the density of the fluid. Well, what we can see is we have kilograms per meter cubed by meter cubed per second, which will give us units of kilograms per second. And this here is the mass of fluid flowing through that surface per unit time. And if we look at the more general case, where we have the surface being oriented at some angle to the fluid, so we may visualize this by looking at the side view of the surface and looking at the normal vector to the surface. So this angle is equal to this angle. So in 3D, we can visualize the normal to the surface being perpendicular and looking something like this, and it has some angle to the fluid velocity vector. So in general, the volume flux of a fluid is equal to the dot product between the velocity vector of the fluid and the oriented area vector. And by the definition of the dot product, that's equal to the magnitude of the velocity by the magnitude of the area multiplied by cosine of the angle between the fluid velocity vector and the normal vector to the surface. So if we draw the velocity vector like this, then we can visualize the dot product, which is basically the projection of the fluid velocity vector in the direction of the normal vector to the surface. So only the perpendicular component to the surface contributes to the flux, because the parallel component does not flow through the surface. So if we look at the extreme cases, for theta is equal to 0, so what we can see is the fluid velocity vector is in the direction of the normal vector, and therefore the flux will be at a maximum. So all the fluid will flow through that surface area. Whereas if theta is equal to pi on 2, so this case looks something like this. The normal vector to the surface pointing in that direction, and the fluid velocity vector pointing this way. So in this case, the flux is going to be 0. So no fluid is going to flow through that surface, in other words. Now translating this concept to electric flux, well, electric flux is defined as the dot product between the electric field and the area vector, which again, using the definition of the dot product, is E by A cosine theta. So note that the electric field does not flow. So for an electrostatic charge, the electric field looks something like this, and it's static. But basically the electric flux is the amount of electric field that's going through the surface at some distance r from the charge. So if we look at some differential area on that sphere, well, the electric field is always perpendicular to the surface of the sphere. And therefore we can write the differential electric flux is equal to the dot product between the electric field and the differential area element. And if we integrate both sides of the equation, we get the electric flux is equal to the integral of the dot product between the electric field and the area vector. And now if we look at our special case, well, we know the electric field for a single positive electrostatic charge, so that was equal to 1 over 4 pi by the permittivity of free space multiplied by the charge on the radial distance to some point in electric field squared. And now if we want to calculate the electric flux through that spherical surface at some distance r from the charge, well, that's equal to 1 over 4 pi epsilon naught by q on r squared, which is the electric field at point r, and we multiply this by the area. So the surface area of this sphere is 4 pi r squared. And now we can cancel 4 pi, and we can cancel r squared, and this gives us q on epsilon naught. So in other words, the electric flux through a closed surface, so we define this as the integral of the dot product between the electric field and the area vector, as we've done more generally before, and we put a circle on the integral to indicate that we're integrating over a closed surface. And as we obtained for our closed surface over here, and let me get rid of this for a second, we got the electric flux was equal to Q, and specifically the charge enclosed within that surface over the permittivity of free space. And this here is our general expression for the electric flux through a closed surface, which is obeyed for any closed Gaussian surface. And this can be proven using more advanced calculus, such as Gauss's divergence theorem, but we'll just take it as it is for now, and we'll apply it to determine the electric field for different charge distributions. And I'll see you in the next video.